Hi class. Well, I gotta say, that was one of the most frustrating days. I was so excited about this lecture. Um, because we are going to talk a little bit about something called superposition. Um, it's kind of an exciting thing, but we'll talk about the superposition thing next week. What I want to get to you guys for homework this time is all about the catapult. So, where we started class was the idea that this was a military application and that there are other military applications like the DARPA Robotics Challenge that are still funding research today, and that the people who had come up with answers at the time, contemporaries to Galileo, were pretty far off. They knew that it would go up, and people close to it saw that it would go pretty much straight up, kind of thing, but then they had this very weird shape to the arc that didn't really play out. It didn't really represent what was going on at all. But Galileo had studied Archimedes, and he knew about the conic sections, and he knew them very well. He and Kepler, because they both knew the conic sections very well, go back and forth, and Kepler is going to talk about the ellipse in the elliptical orbits, and the parabola in the parabolic projectile launching of things with our catapult is probably the thing that Galileo is very famous for. Okay, so we had this idea that he knew how to draw a parabola, this ability to draw a parabola with these boxes comes from the Greeks, and the boxes grow relative to the up, down, and the left, right. Oh, I just see that I forgot to open my Scratch thing, so I'm going to pause this, open our little Scratch file that we did manage to make during class. Hold on. Okay, so we're back. So the boxes that we have, he's dividing, in knowing how to construct his parabola, he's constructing different boxes in different proportions. And he notices that the up-down proportion of the box corresponds very nicely to the things that he's observing in acceleration. The things he's observing in acceleration. The way that the up-down side of this box grows matches what he's seeing with acceleration. Notice that the way this box doesn't grow at all. It's the same width each time, but the length of the box grows. This is if he projected a cannon out here and it fell down to the earth. So if he's doing it at horizontal, if he shoots it out horizontally, this is how it would fall to the earth. Okay, so we've talked about him and his acceleration in the up-down way. Now we're going to add the side to side, and we're going to hopefully see a parabola. Okay, so in class I'm going to reconstruct the stuff, and there's a little note, there's a comment on the thing, so you guys can, once this is all done, you can. I encourage you to remix it if you're a Scratch person. If not, just play with it. But let's start with where Aristotle said. Aristotle said that you fall at a certain velocity. We're going to have let me set the stage with our backdrop. Our up-down, of course, we're going to talk about this actually in a little bit when we get to Descartes, but we have an XY grid, and our up-down is Y, and our left-right is X. Actually, let me get a little different one, because we're not exactly going to start. So up and down is Y, left and right is X. And Aristotle says when you're falling, heavy things fall at a certain velocity. And what that would mean is what we're going to do is we're going to set our velocity in y, which is the rate at which this is what Aristotle said, not what's right. Our velocity in y, we're going to set it to a -2, and that's going to be constant forever. And the way that our guy is going to fall is forever, until he was touching the ground. He's going to change y by that velocity. By that velocity in y. Right, and we press green, go. Oh! I have to press the space bar. There he goes, at a constant velocity. All right. But that's not what Galileo observed. Galileo observed that you fall faster and faster and faster, and that is acceleration in y. So we're going to take this other variable, acceleration in y, and we're going to make it -2, and we're going to start out at 0, because we said when you first drop something, its velocity is 0, and it speeds up as it goes. So, and instead of just changing by velocity in y, we need to, every time we go through, we're going to change velocity in y by acceleration in y. And let's see how that looks. Oh, it fell much faster, because at each second he's speeding, the rate at which he's falling is speeding up faster and faster and faster. Now, if we were to shoot him out of a cannon instead of drop him, and we were to shoot him straight up into the air, he would have a certain velocity from the gunpowder, but he wouldn't have an acceleration from the cannon. He'd just have a velocity after the impulse. There's a whole technical term for that, but it's called. But anyway, so we would give instead of setting his velocity in y to 0, let's set his velocity in y to 15. He's going up out of that cannon really fast. He's going straight up, and his acceleration is -2. Let's see what that looks like. So now we're going to fire him out of a cannon. He goes up and he falls down. All right, so we had to make this gravity much less. And get to Asher's -0.5. There we go. So he's going up and then he comes down. But he's going straight. He's going up and goes straight down. Now this is where we get to the vector part. We'll talk more about next week. But there is a way using Pythagoras, and I'm just going to have you review the Pythagorean theorem this time. Using the Pythagorean theorem, we can separate the up-down from when we go at an angle. We can separate it, make a right triangle, and now we're going to tilt the cannon so some of the velocity is going up down and some of it's going over. So let's see. We'll just randomly set the velocity in x to, we'll say it's over 2. For every 15 up, he's going over 2. And we'll need to change x by velocity in x. Reset them. See what we get. Alright, we get a beautiful parabola. Now we can make that parabola wider. Let me make him, I'll make him start someplace lower. -110. Okay. There we go. So I hope you'll play around with it and change different things in the velocity. Now, if we wanted to, I'm going to run out of time, but there's no acceleration in x right now because there's no force pushing him. He's in motion. He's going to tend to stay in motion unless acted upon by an outside force, and that's different. It operates differently in x and it operates differently in y. We'll talk more about that and the exciting superposition stuff I worked on all last night with a bunch of guys from Physics Forum. But we'll talk about that all next week when we actually get to week 9. But this should give you enough to make some beautiful parabolas with your homework. I hope you have a good weekend and that it makes up for today. Talk to you soon. Bye.